2.5 million light-years from Earth, something watches back. Nearly 1 trillion stars pack into the rotating disk of the Andromeda Galaxy, stretching 220,000 light-years across. Our closest large galactic neighbor hurtles directly toward us at roughly 250,000 miles per hour. For more than a century, astronomers believed they had mapped this cosmic island. They charted its spiral arms, tallied its globular clusters, fixed its distance, and pieced together its history of galactic cannibalism. They assumed its center held a quiet giant, a dormant supermassive black hole simply curving space-time in silence. Then the James Webb Space Telescope directed its infrared gaze at that core. What it uncovered defied expectations. It displayed unusual radiation bursts, distorted gas clouds, infrared bright dust rings marked by gaps and asymmetries, and filaments of superheated material spiraling inward faster than gravitational models allowed. It revealed a monster that may no longer be sleeping. At the same time, fresh evidence confirmed Andromeda has swallowed between 100 and 200 galaxies across 12 billion years, that its halo still bears the scars of those conquests, and that our own Milky Way already interacts with Andromeda through overlapping halos of hot gas reaching nearly 1 million light-years in every direction. The terrifying signal is not merely radiation. It is activity, movement, acceleration. Let's begin at the center. At the exact center of Andromeda sits a supermassive black hole with a mass estimated at 140 million times that of our Sun. By comparison, Sagittarius A** at the Milky Way's center holds about 4 million solar masses. Andromeda's central black hole is therefore roughly 35 times more massive. For most of recorded human history, it has been labeled inactive. No blazing accretion disk surrounded it. No overwhelming radiation flooded the electromagnetic spectrum. It was considered quiet. Yet observations from the Chandra X-ray Observatory started shifting that view. Since 2000, Chandra has tracked the galactic nucleus and recorded a weak but steady X-ray emission. Occasionally small flares flared for hours or days before fading back to baseline. In 2006, something changed. The X-ray brightness surged by a factor of 100. The region flooded with high-energy radiation before dimming again. In 2013, another powerful flare struck. This time, the event aligned with a burst of neutrinos detected by the Ice Cube Observatory in Antarctica. Neutrinos form in extreme environments where matter is ripped apart by immense forces. 2 major X-ray flares and 2 neutrino bursts from the same source pointed to violent processes unfolding in Andromeda's core. A 2025 analysis confirmed that since 2006, the baseline X-ray emission has stayed elevated and that flares have grown more frequent. These are confirmed observational data. The black hole behaves differently than it did 2 decades ago. The question is not whether it exists. The question is why it is changing. The James Webb Telescope supplied a crucial extra layer of detail. Unlike Hubble, which sees mainly invisible light, Webb observes in infrared wavelengths and penetrates dense cosmic dust. When it studied Andromeda's nucleus, it uncovered long filaments of gas and dust spiraling toward the center. These structures glow in infrared because they heat up as they fall inward. Friction makes the gas rub against itself, raising temperatures to thousands of degrees. Still cooler than the millions of degrees near the event horizon, they are hot enough to shine strongly in the wavelengths Webb detects. The feeding process is not steady. It happens in bursts. Large masses of gas spiral inward over weeks or months, triggering radiation spikes before the black hole settles back into relative quiet. What stands out now is the rising frequency of these feeding episodes. Some filaments move faster than gravitational models alone predict, suggesting additional forces, magnetic fields, or pressure from outflows, may be steering their motion. Near the center, the region turns chaotic, ordered spirals breaking into turbulent vortices as material nears the accretion zone. Webb cannot resolve the event horizon itself, but the outer filaments tell the story plainly. More material reaches the core now than in previous decades. The monster remains mostly hungry, yet it feeds more often. Galaxies are not peaceful islands of light. They are gravitational battlegrounds where the strong devour the weak. And Andromeda is no exception. Direct evidence of its violent past is etched into its halo. The vast faint sphere of ancient stars and dark matter stretching hundreds of thousands of light years beyond the visible spiral disk. Using deep-field observations from the Hubble Space Telescope, astronomers mapped dozens of stellar streams arcing through this halo. These streams are not random. They are the stretched remnants of smaller galaxies that plunged into Andromeda's gravitational well and were ripped apart over millions of years. When a dwarf galaxy is captured, tidal forces stretch it into long ribbons of stars that slowly disperse along its orbital path. The original galaxy disappears, but its stellar stream lingers for billions of years as a ghostly trace of what once existed. By studying the ages and chemical compositions of stars inside these streams, astronomers reconstructed Andromeda's merger history. The results are striking. Over the past 12 billion years, Andromeda has devoured between 100 and 200 smaller galaxies. Some are modest dwarf systems holding only a few million stars. Others were substantial spirals containing billions. Two major mergers stand out. One took place roughly 10 billion years ago with a galaxy perhaps one-fifth the mass of the Milky Way. Another significant merger occurred about 2 billion years ago, sparking bursts of star formation and reshaping Andromeda's structure. These are confirmed chemical and kinematic signatures locked inside the stars themselves. Andromeda did not grow quietly. It built itself violently. Another layer of evidence comes from Andromeda's population of globular clusters. These dense, spherical collections of ancient stars orbit the galaxy like relic satellites. Andromeda holds more than 400 confirmed globular clusters, far more than the Milky Way's roughly 150. The number of globular clusters tracks directly with a galaxy's merger history. Each time Andromeda consumed a dwarf galaxy, it inherited that galaxy's globular clusters. By following their orbital motions, astronomers found these clusters fall into distinct populations. Some orbit in alignment with Andromeda's primary rotation and likely belong to the galaxy's earliest formation. Others trace highly inclined or even retrograde paths, showing they were captured during mergers. Studies published in 2019 revealed that the captured clusters split into at least two subgroups, matching the two major merger events identified in the halo, one from about 2 billion years ago and another from roughly 10 billion years ago. Their chemical compositions confirm separate origins, since stars born in small galaxies display different elemental abundances than those formed in larger systems. Infrared observations from James Webb have let scientists measure the temperatures and ages of individual red giant stars inside some of these clusters with unprecedented precision, sharpening the timeline of Andromeda's cannibalistic past. Even now, multiple satellite galaxies remain trapped in Andromeda's gravitational field, some already showing stellar streams that signal active tidal disruption. The process continues. Andromeda is still feeding. For decades, astronomers described the collision between the Milky Way and Andromeda as a distant future catastrophe set roughly 4 billion years from now. It was portrayed as something so remote humanity would never witness it. That description no longer holds. In 2020, scientists on the Omega Project, which uses the Hubble Space Telescope to map ionized gas in Andromeda, made a startling discovery. The hot ionized gas halo surrounding Andromeda stretches nearly 1 million light years from its center in every direction. This halo consists of extremely diffuse plasma heated to hundreds of thousands of degrees and remains invisible to conventional telescopes, detectable only through its absorption of background ultraviolet light. The Milky Way possesses a similar halo of hot gas and dark matter, extending roughly 1 million light-years outward. Andromeda lies approximately 2 million light-years away. The implication is straightforward and grounded in direct measurements. If both galaxies have halos extending 1 million light-years, then their halos are already overlapping. Observational evidence indicates this interaction has likely been underway for more than 1 billion years. We are not waiting for first contact. It has already begun. The interaction stays subtle because the halo gas is extremely tenuous, only a few atoms per cubic meter, and exerts no noticeable drag on the galaxies. Yet, gravitationally and structurally, the two systems are already linked. They are not isolated islands drifting through empty space. They are joined through vast envelopes of hot plasma and dark matter that have started to mingle. Simulations show that over the next few billion years, this interaction will intensify. As the halos compress where they overlap, they will heat further and gradually reshape the visible disks of both galaxies. Earlier models predicted that in about 3.7 billion years, the two spiral disks would pass through each other for the first time, triggering massive bursts of star formation as gas clouds collide and compress. After separating temporarily, they would collide again, eventually merging into a single elliptical galaxy roughly 7 billion years from now. This merged galaxy has been informally named Andromeda. However, more recent research published in 2025 using data from the Gaia satellite and Hubble added uncertainty to this timeline. When factoring in the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, the probability of a full merger falls to about 50% within the next 10 billion years. It is possible the galaxies may simply pass by each other without fully merging. What remains certain is that the Milky Way and Andromeda are gravitationally bound and closing at approximately 250,000 miles per hour. The halos interact now. The final outcome stays uncertain. The dance has already begun. Even if the climax lies billions of years ahead, should the Milky Way and Andromeda ultimately merge, the most dramatic event will not be the collision of stars. Direct stellar impacts are extremely unlikely given the vast distances between them. The true climax will unfold at the center of the newly forming galaxy. The Milky Way's supermassive black hole, Sagittarius A*, with a mass of approximately 4 million suns, will eventually meet Andromeda's 140 million solar mass giant. At first, the two black holes will orbit each other at distances of tens of thousands of light years as their host galaxies interpenetrate. Over millions of years, gravitational interactions with surrounding stars and gas, a process called dynamical friction, will steadily strip them of orbital energy. As their separation shrinks to only a few light years, gravitational wave emission will dominate, driving their inward spiral. They will circle each other faster and faster, radiating energy in the form of space-time ripples traveling at the speed of light. In the final phase, the two event horizons will approach at a pace that accelerates dramatically. In the seconds before merging, they will orbit each other hundreds of times per second at significant fractions of light speed. This is not speculative fantasy. The emission of gravitational waves from merging black holes was predicted by Einstein and directly observed by LIGO and Virgo in 2015. The difference here is scale. Instead of stellar mass black holes, this will involve Titans millions of times more massive. When the two supermassive black holes finally merge, the event will last only a fraction of a second. Their horizons will fuse into one larger black hole, but the process will not be instantaneous or calm. The merged object will oscillate violently, a phase known as ring down, emitting a final powerful burst of gravitational waves before stabilizing. The final mass will be approximately 144 million solar masses, the combined total of both black holes. However, between 1 and 5% of their mass may convert directly into gravitational wave energy during the merger. That energy will propagate outward across the universe, carrying precise information about their masses, spins, and orbital parameters. If the two original black holes possess different spins or masses, the merger can produce a gravitational recoil. This kick could propel the newly formed black hole away from the galactic center at speeds of hundreds or even thousands of kilometers per second. Simulations suggest such events are physically plausible and may have already occurred in other galaxies. If this happens in the future Milky Way Andromeda merger, the resulting galaxy could temporarily lack a central black hole until the displaced object eventually falls back toward the core. These are consequences grounded in gravitational physics. The collision of two supermassive black holes would not simply reshape a galaxy. It would ripple through space-time itself. 2.5 million light-years away, Andromeda is not silent. The James Webb Space Telescope did not detect a message carved in radio waves or a coded transmission from another civilization. What it detected is something far more unsettling: change. Increased X-ray activity. Neutrino bursts aligned with flares. Infrared bright filaments spiraling inward at velocities beyond simple gravitational expectation. Dust rings warped and disturbed. A supermassive black hole that has behaved differently for nearly 2 decades. The signal is not a sound. It is a pattern showing that the 140-million solar mass black hole at Andromeda's center is feeding more frequently. A pattern confirming that this galaxy has spent 12 billion years devouring between 100 and 200 smaller galaxies, inheriting their globular clusters, scattering their stars into tidal streams that still haunt its halo. A pattern revealing that our own Milky Way is already interacting with Andromeda through overlapping halos of hot ionized gas, extending nearly 1 million light-years in every direction. The collision once described as a distant future event has, in a very real sense, already begun. The halos are touching. The gravity is binding. The approach continues at roughly 250,000 miles per hour. The final outcome may be uncertain. Perhaps a merger in 4 billion years, perhaps a near miss over 10 billion years. But the gravitational dance is underway. And if a merger occurs, it will culminate not just in distorted spiral arms or bursts of newborn blue stars, but in the spiraling approach of 2 supermassive black holes. Their eventual collision would release gravitational waves carrying up to 5% of their combined mass as pure energy, rippling through space-time itself. Right now, the Andromeda black hole is not fully awake. It is feeding in bursts. Filaments glow in infrared. Flares appear more often. The baseline radiation is higher than it was 20 years ago. The monster is not raging, but it is stirring. And that is what makes this terrifying, because galaxies do not change quickly by human standards. When something shifts on this scale, it means a process millions of years in motion is accelerating. We are watching the early movements of forces that will outlive our species, our planet, perhaps even our sun. The terrifying signal from Andromeda is not a warning of immediate destruction. It is proof that the universe is dynamic, violent, and already in motion. And we are part of that motion. If you want to follow the real cosmic events unfolding in real time, the black holes feeding, the halos merging, the galaxies preparing for impact, subscribe and stay with us. Because the next signal from Andromeda may not just rewrite textbooks. It may redefine our place in the cosmos. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.